Looks like it's time. Welcome back, everyone. We're now on week 10 of 16 weeks, so we're definitely cruising through the class. Any questions or comments to start us out today? Okay, I guess the bigger announcements is that all exams have been graded, and so far on this exam, the average came out as 78.9%, and the maximum obtained was 100% on this exam. Congratulations to that student. I'll have exams returned when we come back on Wednesday's class. And I intend to also post the solutions as well. But any other questions that folks would like to discuss? Okay, well, with where we're at so far in the schedule, we're moving through our tests. Here we're going to be looking at the integral test. We really just have one last problem to take a look at or finish off. Right after, we're going to be dealing with the comparison tests. And that's starting to fill out most of our tests. We'll have alternating series, something called ratio test, root test, for some more esoteric things. But before long, we're going to be dealing with power series and representation of functions using power series. So we're getting towards the interesting parts of chapter 11 quite rapidly. One thing you might notice when you're doing the reading in these sections is that the homework sets don't have a whole lot of applications. And the reason for that is all this work we're developing is towards a very specific purpose of Taylor series, Maclaurin series. That is the ultimate goal and application to all of this work. So with where we left off, we are right here. That wasn't the last one. We did part F before we went to the weekend, just because it was fast enough at the time we had. And on this one for part E, we have a complicated looking series, tangent inverse with the n squared plus 1 in the denominator. And let's think about what the right test could be. A lot of times people really like the test for divergence because it feels like it's super applicable. But it turns out it really isn't. A lot of the series that we actually investigate have the property that the limit is 0, which is unfortunate. But just to illustrate on this one, let's attempt the test for divergence and just see what happens. I'll use the orange pen, which just makes it look like it's not our official answer, it's more just notes. We'll be using test for divergence. And the test for divergence always goes the same way. You go over here to the series, take the nth term, which is right there by the red dot, and calculate the limit as n goes to infinity. For tangent inverse n, divide by n squared plus 1. Now, to think about this limit, we need to know what happens in the numerator, tangent inverse n. So here's a quick graph. When you go towards the right end, because we're taking the limit as n goes off to infinity, the relevant graph looks like this. We might as well put all the asymptotes on, why not? There's a horizontal asymptote at height pi over 2. Then there's another one at height negative pi over 2. So when we plot tangent inverse n, it looks about like this. This is a graph of y equals tangent inverse x, because the dots are connected. We can't say n. This is now an actual function. But as n gets larger and larger, it tells us the numerator is bounded. It's only going to go up to pi over 2, equaling pi over 2 in the limit. Denominator is unbounded, though. It grows without restriction towards infinity. So if we have something growing unbounded in the denominator and something that's heading towards a finite quantity in the numerator, the whole limit would go to 0. And that's really unfortunate because then it tells us that didn't happen. The limit exists and it is 0, so the test fails. Which is unfortunate, but it's good to study the case when the test doesn't work, because this is one of the most misunderstood tests of all. It's easy to apply it when it does not apply. Getting a value of 0 does not tell us that this converges, for example. Well, if the test for divergence is out, we could try the geometric series, except it cannot be geometric and would have to be an exponent, not a base. Definitely not a p series. Well, there's an n squared, which looks nice, but the numerator and denominator, the plus 1 and the tangent inverse n, exclude it from being a p series as well. All that's left is the integral test. So we'll practice that one once more and give this a try. So the way the integral test goes is we take this and define a function. Let's say let f of x equal tangent inverse of x divided by x squared plus 1. But we also need to be really careful with this function because not all functions work. It has to be continuous, positive, and decreasing. And any one of those things failing, down here, might as well highlight it, will mean that the test does not apply. For example, if our function is always negative, we have a big problem, but we are okay. We're taking a limit as x goes to infinity. Over here, when we go to the improper integral, we'll put in a new parameter t, but the values for x are always going to be large in this context. The numerator is going to be positive quantities, and so will the denominator. So we can say f is continuous. It's a ratio of continuous functions, both continuous on the entire real number line. It's positive on the right domain. If you're only looking at positive values, starting at x equals 1 to infinity, for example. And what else do we need? It has to be decreasing. Forgot how to spell decreasing. Give me a moment. On the domain from 1 to infinity. Decreasing is sometimes hard to tell, but I think it's not too bad to resolve on this one. If you look at what's going on here, the limit was 0 because it is a decreasing function. We have finite values in the numerator, and as the denominator gets larger and larger, values of f of x get smaller and smaller. So we are decreasing on the domain from 1 to infinity. So that means we can use this part. If the improper integral from 1 to infinity converges, so too does the series. And likewise, if it diverges, so does the series. So convergence or divergence of this now depends on the convergence or divergence of this integral. We're going from 1 to infinity of f of x dx. So finally, here's where the integral test really starts out in earnest for that function there. Any questions, folks, before we go through that improper integral? Yeah.
We could write out the let f of x equal whatever, and then continuous positive decreasing on like the test.
I would say if you omitted that, that would be okay. This is more for us to make sure we're hitting all the hypotheses for sure. But yeah, you don't have to do it exactly this way. I would say other things that we have to watch out for are things like, say, if it's a geometric series test, we have to put down this part right here as part of the work, and then say converges and indicate the test. But for this kind of stuff, not as important, I'd say. Other questions at the moment? Okay, so we've checked the hypotheses. Now when we go to this integral, we do have to analyze it as an improper integral. So the very first step is to convert it into a limit as a new parameter t goes off to infinity. So we're integrating from 1 to t. Again, the logic in that is you can't use the fundamental theorem of calculus part 2 at all here because infinity is not even a number. But t is, we're just insisting that t gets larger and larger in the limit, and fundamental theorem works right here. Let's plug in the function tangent inverse x. Divide by x squared plus 1 dx. Once we get to this stage, we now have to analyze this as an improper integral, which means we need an antiderivative by the red dot. And this is a good u substitution type of problem. We could let u be equal to tangent inverse x. Reason that works out for this one is the differential du is 1 over 1 plus x squared is how the author often writes it, but if you wrote it as 1 over x squared plus 1, just as good. It's a differential, so it still needs dx. But that means all of this right here is going to turn into du. This part right here is just u itself. And so on our next step, it's the limit as t goes off to infinity of integrate from, oh, yes, there's a little bit more going on here. Let's change our limits of integration as well before we forget. It goes from 1 to t, but that's for the variable x. X equals t, x equals 1. So for a new variable u, we plug our values of x right here by the red dot. So u is going to be tangent inverse t on the upper limit of integration. We can just write that in now. Tangent inverse t. A lower limit of integration is tangent inverse of 1, but that has a nice value. That turns into a pi over 4. So we're going from pi over 4 up to tangent inverse t for the integral u du. So finally, we're on the right track. We can get the antiderivative, evaluate it, take the limit. Any questions to this stage? Okay. Antiderivative of that is 1/2 u squared. So I'll put the half in first, way in front of the limit. As t goes to infinity, u squared goes in here, and we evaluate from pi over 4 to tangent inverse t. And scroll a little bit. Now it turns into 1/2. Limit as t goes to infinity. Let's put a big bracket here. First evaluation is tangent inverse t squared. Minus second evaluation, we're plugging in pi over 4 into that location. So minus pi over 4 squared. We still have to resolve this limit, but that's the picture for it right up here. As t goes to infinity, tangent inverse t is following this curve, so we're getting a value of pi over 2, and then it's just going to be squared in that location. So from up there, we now have 1/2 pi over 2 squared minus pi over 4 squared. We could do a lot of arithmetic on this to find out its simplified quantity, but all we wanted is to know whether this converges or diverges. If we put down a finite number like this, that's enough information for us to say improper integral right here converges. Now the integral test says if your improper integral converges, then this thing, just putting it here so I remember what it was. I guess I should have known just by looking over here. You just put it in instead for x. We can now say that this all implies summation as n goes from 1 to infinity, tangent inverse n divided by n squared plus 1 must also converge. Deserves an exclamation mark since, I mean, if this was a big kind of weird math joke, that's the punchline. Convergence of the improper integral right over here implies the series itself must also converge all at the same time. That means we did it, folks. That's the resolution to this weird series right here. Any questions about it so far? Okay, so the integral test, the one thing that I would want to always kind of remind people about is it is the test of last resort, because as you can see, there is a lot of steps in getting through an integral test. If you could find a way to analyze this as a p-series somehow, some way, the work would have been far less. Because how does a p-series go? You just state the power. Let's take a look at that. We did a p-series on this one. You just state what the power is. If it's less than 1, you have divergence. If it's greater than 1, like on this one, you have convergence. So everybody loves p-series. They're extremely rapid. And the integral test, you try to apply that to every single problem on an exam, you could run out of time very easily. It's so much steps. So what we're going to do next is put another set of tests on the table called the comparison tests. That's 2 of them, which is going to allow us to occasionally take something like that series here in part E and actually analyze it as if it was a p-series by comparing it to the correct p-series. So that's what we're going to be doing very next. But any last questions or comments, folks, on the conclusion of these notes? Okay, let's take a look at then. Oh, sorry, question first.
No, worst case scenario, go past on pretty much most of these, to see if they convert.
I would say it wouldn't be most, because the one thing that's actually more restrictive than it looks like is the requirement that F be a positive function. So that goes wrong whenever you're looking at, say, maybe. Forgot what I swear. It goes wrong when we're looking at, oh, these are all integral test problems. It goes wrong when we're looking at something like, I'm gonna have to dig deeper. Something like this kind of stuff. So integral test fails on this one really badly. And that's because the series is alternating from positive to negative. We're gonna have lots and lots of alternating series, but I guess I could water down that comment. Even on these notes, a lot of stuff you could analyze as the integral test, but that means you have to find an antiderivative of stuff like this, which could be actually pretty hard on its own. So that's another downside. So I guess the two big downsides are you have to have positive functions. So anything alternating is a big problem. And you've got to be able to find a readily available antiderivative. Say for a really quick example, series that goes this way, e to the n squared is very problematic for the integral test because the antiderivative e to the, let me put in an actual x squared, dx, has no elementary, this is our author's wording, antiderivative. Which means we can't just write down a function. It's going to be, it turns out the antiderivative of this, which is a little bit better than the fundamental theorem of calculus part 1, is a power series. That's the better answer. But other questions at the moment? Okay, well, let's save this up. And next we're going to go to those comparison tests, section 11.4. It's always kind of amazing how much Word struggles to open and close these things. So the notes in section 11.4 are actually kind of short compared to what we've been doing already in the past. Would say section 11.2 in particular is pretty tricky because we're bridging the gap between sequences and something related but feels totally different, series. 11.3 is also tricky because the integral test is just technical, a lot of steps, a lot of conditions. When it comes to the comparison tests, I really don't have a whole lot to say. This is really the whole test right here. I guess we could say a little bit about what the logic is on these tests. On both cases, we suppose we have sequences with positive terms. Again, that's pretty restrictive. If all the terms were negative, we could factor out the negative sign and still have positive terms. But if the terms alternate positive, negative, it tells us comparison tests can't be used at all. That's kind of unfortunate. Well, that's okay. Here's how it goes. There's two cases. Either the series relative to Bn converges or it diverges. But if we have, say, converges, for example, and we know that the series we're interested in has terms always less than or equal to the terms over here, we say that the series AN has to converge. So in other words, thinking of that in a different way for part A, if the series Bn converges, and this is a really just fast shorthand if you have to write this out. Sometimes our author goes like this, it just says summation of Bn, not mentioning where it goes from, just as a really fast way to refer to the series. So if the series converges, and the series for AN is always less than or equal to the series for Bn, because of this inequality, just a different way to visualize it, this means AN converges. Now, why is that? That's because the statement right here of convergence, together with inequality, says the sum over here is going to be less than a convergent series, forcing this to converge as well. Essentially, it's this inequality, but I threw the summation symbols on it, just in case that's a better way to visualize it. If you turn it all around and say, in part B, if the series for Bn diverges, and we have to estimate a different way. Notice what we're saying this time. All of the terms of the series are larger when it's An than Bn. Visualizing it differently, we could say summation An is bigger than or equal to summation of Bn. Let's hold that thought. Well, if Bn diverges and the terms for An are larger than a divergence series, then that must mean An has to also diverge. It's diverging even faster, in other words. So this implies summation An diverges. So that's just another way to think about the test. Some people prefer to just think about that inequality and then come back to the big punchline. Other people visualize it this way, the total series being estimated in that way due to the inequality still. Well, that's how the comparison test goes. It's honestly kind of tricky, and the trickiness in the comparison test is that stuff, making estimates. That's something that you do a ton of once you take other math classes. If you're pursuing, say, a minor or major in mathematics, you eventually have to take elementary analysis, and this is what makes elementary analysis difficult, those kinds of estimations. So let's give this a try. Example 1 says, test the series for convergence divergence. I've been putting this on the lecture notes as well as the homework sets just as a reminder. The way these things are graded is a point for saying the final conclusion, convergence divergence, but that's going to be for all series tested. Because we're doing a comparison test, we're actually testing 2 series all at the same time. The thing we're comparing it to, we have to come up with Bn and do a test on it to know if Bn converges or diverges. And then the final test will be a comparison test. That's why it says all series tested. Then we do have to show all steps of the chosen test, and that's going to be for each test we use. So here's how it goes. If you look at this thing right here, 1 over n minus 3, we want to compare that to something. And it looks like it could be, say, very similar to a harmonic series. Harmonic series would have gone this way, summation 1 over n. It's the n minus 3 that makes it not a harmonic series, in fact. So here's the way we start estimating. Start with your n minus 3 and compare it to something you'd rather see in that denominator. This would be easier if it was just an n. We would have said diverges by the harmonic series. So compare that to n, and we have a less than direction. Notice I'm focusing on the denominators first. That's because I find estimations with inequalities tricky, but if you can break it down into stages, it can sometimes resolve how it should go. So if you have an inequality going that way, less than, and you take the reciprocal of both sides, you flip the inequality. It's now a greater than. So reciprocal on the left, 1 over n minus 3, reciprocal on the right, 1 over n, gives us 2 things. On the left, that's the nth term of the series, 1 over n minus 3, so that's nice. On the right, that's Bn from right here. It's a series that diverges, but we have to actually say that, so it's a really fast statement. We have to say the name of the test if we use a test, but this is an exceptional case. This is one series that has a name, and we just know the conclusion on it. We would say something like this. Summation, as n goes from 1 to infinity, Bn is summation as n goes from 1 to infinity, 1 over n, is the divergent harmonic series. You could analyze this as a p series if you wanted, however. You could say, this is a p series with p equals 1, and we would go and say 1 is less than or equal to 1 right here, so it'd be divergent if you decide to use the p series test. The harmonic series comes up so often, it's just fine to say it's divergent because it's harmonic series, and that's would be totally fine. But now let's look at what we have so far. We have the terms an are always larger than the harmonic series terms bn. So if we have that case and bn diverges, we're in this situation. Summation of an is larger than the summation of bn, and diverges even faster towards infinity. So that's our final conclusion. Because of this inequality, we could say this implies summation an, which is a summation as n goes from 4 to infinity. I just noticed that 4 is important because you can't put in a 3, for example. So it started at 4, which means over here, technically, it should have been as you go from 4 to infinity, not a 1. I wouldn't say that's a huge logical problem, but it is a logical problem. Our series have to start at the same index. Sorry for that change right there. Don't forget n equals 4 is the starting point for bn. So this one right here, which is 1 over n minus 3, also diverges by the comparison test. So we did it, folks. This one, you could have used the integral test on this thing. That's because the term's always positive, it's always decreasing, and it's a continuous function, thanks to starting at 4. But that's a long, slogged out process. If you know it's extremely similar to the harmonic series, and you can get that estimate to work out, showing the terms are always larger, your work is done. You just test the series you compare it to and make your conclusion. Any questions at all, folks, with the conclusion there? Okay, so this is the value of really good theorems, and this is a nice one. It can take something that is a lot of computation, a lot of thought, and make it a really, really fast resolution. But it is a tricky test, so let's take this with us as we go and see how it works on the next problems. So that was part A. We were suspecting divergence on this one. And now part B, it has a little bit more going on. If you look at it, it's n divided by n cubed, essentially, for very large values of n. Those are the dominant terms. N divided by n cubed turns into a 1 over n squared. That means if we can compare this to a p-series, our work is done, essentially. So this one looks like it ought to converge, which means we're trying to estimate this way. We're trying to get less thans to work out for us. If we start with our denominator, we could say n cubed plus 1 is bigger than n cubed. Certainly it's true. We take the reciprocal, we have 1 over n cubed plus 1 is less than 1 over n cubed. So that's focusing on just the denominator so far. We pull in the whole function, we can now say n minus 1 over n cubed plus 1. We want to say less. We already know that the denominator with a less than is resolved if we put in n cubed. But what about the numerator? N minus 1 is definitely less than n, so that is an easy way to estimate. We can still just say less than across that way. But once we get to that step, we're now in business because that's an on the left. And on the right, that's the thing we're comparing it to, bn. So once we get this comparison out, notice the critical thing about any way we do this is that inequality sign right there. So we must show this on homework and exam questions. This is part of the work for using the comparison test. And honestly, it's what makes the comparison test a finicky choice. It's fantastic when it works well, and it can be kind of a nightmarish test if the inequalities just don't seem to be working out. These ones are just strict less thans because of this estimate right here is always strictly greater than. But if they came out this way, maybe some other function made it possible they're occasionally equal, we would just carry over the inequalities in the same way. In fact, this is greater than or equal, still a true statement with the or in there. So Our author always states it this way, but if you notice your inequality is actually strict, okay to leave it like that in your work. I think that's more of a stylistic choice for these. Other questions about these? Okay, let's say here, just for help with the work, or excuse me, help with doing these on homework, we must show this estimate. That's what makes the comparison test really get going in the first place. It's not about coming up with this series, Bn is 1 over n squared essentially. It's more about knowing that this series had terms which work out in this way, always less than the terms for the series relative to Bn. So we're still trying to work through the comparison test, but here's the next step. Midway in the comparison test, we suddenly have to do a p-series test, because for this new series, once we write it as a series, it requires a test as well. We're trying to get to this stage, in other words, of the comparison test. So let's write out summation Bn is a summation as n goes from 1 to infinity of n over n cubed, which is a summation as we go from 1 to infinity of 1 over n squared. Now, this is a whole new test, but we have to indicate what the test is. You might just say p-series. If you said that, that's good enough for me to say, indicate you're using the p-series test. You have to show all the work for that test, but that just amounts to find the power p. Give the right inequality, bigger than 1 implies convergence. So we now know that the series for Bn is a convergent one. We found that the series An has terms always less than a known convergent series. Our conclusion is then, we must have convergence for the series An. So let's say here, this implies summation An, which is n goes from 1 to infinity, n minus 1 over n cubed plus 1 must converge by the comparison test. It does feel weird to have to say the comparison test on every one of these, because we kind of know we're using the comparison test, right? But the reason we're doing this on the homework set is because when we go to actually look at the problems, there are 2 comparison tests, and I need to know that you know which one is actually being used. The ordinary one that we're using here, or the next one we're about to specify. The other thing that's new in these problems is that starting in this section 11.4, notice we really did 2 tests. We tested a p-series, and then we did the comparison test as well. That starts to become really, really problem in these kinds of notes, particularly as we go farther along in chapter 11. But any questions at all, folks, getting through this problem here? Yeah.
Like you have n cubed plus 1 and you're comparing it to n cubed. On the other one, you have n minus 3 and you're comparing it to n. Are we just going to use the basic mother graph pretty much of it?
Yeah, pretty much, absolutely. The trouble though is when we get something like, say, this one, there's no great estimate on this one to show great divergence. And on this one, no great estimate to show convergence. So we have to do exactly as you said. We grab just the dominant pieces in the numerator denominator, the terms that matter the most for large n, same as over here. And we just analyze that way in the limit comparison. But it doesn't work for these problems with the ordinary comparison test, because what goes wrong is sometimes those estimates are actually impossible based on how the pluses and minuses were arranged. In fact, that simple change throws the whole thing off, because now it's a +1 here, and my inequality is damaged irreparably. We'd have to use limit comparison. So that's essentially how they all go, and we take that analogy to the extreme on the next test. Other questions at the moment? Okay, let's try out one more then. Well, I mean, we're definitely going to try out one more. Here's the next one of this set. We're going from 1 to infinity, cosine squared n divided by 3 plus 7 power n. hard to know what to make of this thing, but let's imagine we were doing what we were thinking about before. If we were going to compare this to something, we probably want to compare it to a geometric series this time. That's because we have n as an exponent on this thing. But to make it work out, we need a series of estimates. Let's start off with cosine squared. There is a great estimate for cosine. Cosine of n is less than or equal to +1, less than or equal to -1. So that's great because, well, trig functions like cosine have that range from -1 to +1. So it gives this immediate estimate. And notice the power on this really had to be squared because we need positive terms to use the comparison test. Cosine n on its own has positive and negative terms. So square this inequality and we get 0 less than or equal to cosine squared n less than or equal to +1. So that's going to be our estimate for the numerator. In the numerator, cosine squared n is always less than or equal to a 1. That helps us out. Any questions to that stage? Okay, let's pull in the denominator next, that thing. If we have 3 plus 7 power n, that's certainly greater than 7 to the power of n. So we can take the reciprocal of both sides of that equality and say 1 over 3 to the power, 1 plus 3 to the power 7n rather, flip the inequality is less than 1 over 7 to the power of n. So now we can bring in the numerator, cosine squared n. So here's our next step. Cosine squared n, divide by 3 plus 7 power n. We already know we get less than when we put in the denominator, 7 to the power of n. But again, notice how touchy this is. If that was a minus right there, the whole comparison test doesn't work for this. So everything has to be kind of rigged just right. Now that we have that, across the numerator, cosine squared n is less than or equal to a 1. So we can just throw in a 1 there. Now we have two things. On the right, that's bn. On the left, that's an. When we say an, that means we're referring to the original series as summation an. And these little shorthands become valuable for these kinds of tests because we're really looking at two series simultaneously. We need to have a name for both, and that's just the fast name for the original series. Put a summation symbol on that. It'll be the fast name for the series we're comparing to. So let's go and make that happen. Let's say here, comparison test. So that's the big test we're using on the very start of this. You could say that at the beginning or the very end, kind of up to you. But in the comparison test, we have to test that right there as a series. So let's test summation bn, which is a summation as n goes from 1 to infinity. It's 1 divided by 7 to the power of n, but we can turn the whole thing into 1 over 7 power n in that way. That's kind of helpful for us because now if we go to our summary of tests, this document, by the way, I think I might have forgot to mention where it came from. This document is found right here on Moodle, summary for tests. We also had a flow chart. I just decided to park it way down here under exam 3. So for this test right here, we're looking at the geometric series. It has to be something a, RA is a 1, times r to the power n minus 1. The n minus 1 is important only if we're looking for the total sum of the series, which is right there, a divided by 1 minus r. But if all we want is convergence divergence, we look for the common ratio r and just see how big it is in magnitude. Common ratio r here for the geometric series test is that, 1/7. We'll say r equals 1/7, less than 1 in magnitude. So this is convergent. You could say it's a convergent geometric series, or you can just say it's convergent by the geo series test. So however you like to say it, we just have to mention all tests used. Any questions, folks, with resolving convergence of the comparison series? Okay, well, we've got this part converges. we showed the inequality right here because our terms are now less than a known convergent series. It finally tells us original series had to converge. There's no other way around it. So here's our big conclusion. We'll say, therefore, summation an. That's okay if you just leave it like that because it's defined. But I usually in the notes like to be specific. So let me just write it out. Go from 1 to infinity of cosine squared n over 3 plus 7 power of n must also converge. We indicated the test we used just at the very beginning, comparison test, so we don't have to say it again. That would be redundant. I change up how I did it on this one just to kind of convey, when you do these on your own work, it's up to how you'd like to do it yourself stylistically. So you could say your test at the very end, like here, this one converged by the comparison test, or you could just call your shot at the very beginning. That's the test I'm using, it's what you're announcing. Well, any last questions, folks, on how to work the comparison test? Okay, it's a nice test because sure, there could be a lot of writing, lots of things to write out. You're not using the integral test at least, so that's the big takeaway on this one. It's a tremendous alternative. But also notice what's happening in our math class. If you really look at this stuff, there are more words than numbers all of a sudden. And that's kind of how chapter 11 goes. It's an analysis that's referring mostly to the tests, how they're interacting together, and determining convergence or divergence when we stitch together multiple tests at once. So sometimes there's a lot of just ordinary writing like you're seeing here. But we mentioned this stuff doesn't always work out. If that was a 3 minus 7n, that one small change is enough to just damage this whole problem completely. Comparison test wouldn't work because that very first estimate would have been broken. So we need another way when there's just more complicated stuff going on. That's the so-called limit comparison test. This one has a very strange logic that goes along with it. The proof is also really technical, which is kind of unfortunate. But the thought is, if you have two sequences, an and bn, they have to both have positive terms like before, so that's extremely restrictive. We'll have another way to get around that. But if their ratio in their limit comes out as a finite constant c, then the convergence and divergence of both of them are tied together. They either both converge or they both diverge. Only requirement is that c has to be positive as a quantity, and it can't be infinity. It has to actually be a real specific number. So if we got 0 on this thing, the test has failed. If we get infinity or does not exist, the test fails in those cases as well. Kind of the logic about this is, if an converges and bn is so similar that in the limit their ratio comes out as a constant number, then this is similar enough bn that it has to also converge at the same time. And same for divergence. Again, this is a pretty hard one to think about when it comes to its derivation. But if you have the additional time and you're just really bored, I'd say take a look at that. It's one of those things where if you know you're doing lots and lots of stuff with mathematics, it might be a good idea. Well, let's take a look at how it goes. Again, we need to compare our series to something else. When it says both converge or both diverge, that means we also have to test the series for bn to determine its convergence divergence at the same time. But the really big benefit of the limit comparison test is there's no inequalities that we have to estimate. So that allows this one to work. We can't use the comparison test on this one. The signs are too messed up for that. But we can start off this way. Compare to summation bn. So we're looking at this series right here. But we have to come up with the formula for that thing. There'll be a summation as n goes from 1 to infinity. And like we were mentioning and talking about on the last series of tests, the thought is you go to the numerator, imagine what happens when n becomes really large, take the only term that is the most dominant one. That's going to be 2n. We don't need the coefficient 2, we could just take n itself. In the denominator, 3n squared is the most dominant term. When n is large, that's the thing that controls the shape of the curve the most. So we just take an n squared. Then this becomes n equals 1 to infinity, summation 1 over n. So we got the n from here, the n squared from there. And now when we go to test this out, not so bad. It's a p-series. It's divergent as a p-series case. Or you could just say it's the divergent harmonic series. Totally up to you how you'd like to write it out. Let's go this way for the folks that like to analyze it this way. This is a p-series. So we're using the p-series test. That's kind of redundant. We don't have to say it again if you just told me p-series. The power p is 1. There it is, power 1. I like to write this, even though it's obviously true, less than or equal to 1 reminds you those are all of the cases where the p-series diverges. So if you get in the habit of writing that down each and every time, it's going to become like muscle memory. You'll just know that that's the divergent case because it snaked its way into your long-term memory just by writing it down. So it diverges. So that doesn't mean the test is going to work, but what it does mean is we found that Bn diverges, so we suspect An diverges, and the only way to be totally sure is this limit has to come out right, some positive number that's not infinity. So if we did get infinity, it doesn't mean the test is totally ruined. It could mean we just needed something different right here. Maybe we got the wrong values for n over n squared, for example. If we put in a negative n down here, that would totally throw it off. So let's next take the limit. As n goes to infinity, it involves Bn in the denominator, An in the numerator. Let me read you how I highlighted that thing. So here's the An series. So limit as n goes to infinity of the ratio An divided by Bn. Fun fact about this is that's the way the theorem is stated, but it actually doesn't matter what goes into numerator and denominator. Notice the way this is stated. There's no special role of An or Bn whatsoever. You just have to know how one converges or diverges. So when we go to take this limit, as n goes to infinity, what we don't want to get bogged down in is a whole bunch of algebra. So there's a fast way to do this. Write down your terms for An. 2n plus 1, 3n squared minus n plus 1. We're divided by Bn, which just amounts to multiplying by the reciprocal over here. So it's going to be n over 1. Let me highlight that just to convey that's Bn. Then this turns into limit as n goes to infinity of, across the numerator, 2n squared plus n, and across the denominator, 3n squared minus n plus 1. So notice it was a really good idea to simplify here, not just so we can test the series in a good way, but also to simplify the algebra to this stage. Now, here's our common shorthand for taking care of a limit of this kind. That's a rational function in the variable n. Because there's a tie in the degrees, it has a horizontal asymptote found by just taking the coefficient of those dominating portions, the n squared and the n squared. We got a value 2/3. It's bigger than 0. That's the constant being referred to there. And it's not infinity. That's also critical. It's got to be a finite number for the limit to really exist. Once we get that, our work is done. We can now claim, will they both converge or both diverge? We said divergence here, so we say this work implies summation An, which is as we go from 1 to infinity, 2n plus 1, 3n squared minus n plus 1. It must also diverge by the limit comparison test. And like we mentioned before, I'm not opposed to any kind of shorthands you put on this. Like if you put COMP for comparison, that's totally readable. I would know what you meant. Well, that's how that one goes down. Again, this one is pretty much impossible with the ordinary comparison test without extreme amounts of ingenuity. So limit comparison test is our next thing we fall back to. It's really fast in the sense that you just have to resolve a limit, not do crazy inequality estimations. We'll try out a few more of these and see how they go. Because it's a brand new test, we'll also work with a screenshot as well, just to see how things are coming together. Any questions at all before we jump to part B? Okay, let's give this next one a try. It's the same idea as before, except that it's just a messier looking series by a lot compared to the other one up here. So when we go to do the comparison test, however, it still starts off the same sort of way. This is the original series, summation AN. We're giving it a name, so when we come down here, we're knowing what we're referring to. And we're going to compare to summation Bn, which is going to go from 1 to infinity. So over here, we're just giving it a name. Over here, we're actually filling it out. It'll have a numerator and denominator. Anyone see what should go up above? We'll come from here. Sorry, say again. Good call. Between the 2k squared and k, for very large values of k, it's k squared that matters the most. You could pull in the 2 as well, but it's the k squared that matters the most. So usually, just to simplify the work, I grab the variable without the coefficient. Same work either way. Now, taking that idea to the extreme and doing it again, in the denominator, the thing that matters the most for large values of k is the 4k power 7. Plus 3 is going to be totally negligible when n is, or excuse me, k is like around 10 power 6, for example. So we're going to take k power 7, I ditched the coefficient of 4, but don't forget it's being square rooted at the same time. So there's a little bit of exponent work to resolve on this one. Let's go down to a new line. It's now summation as n goes from 1 to infinity. Let me just fix that summation. There we go. Denominator is k to the power of 7/2. Because of the denominator of 2, we'll write the numerator as k power 4/2. So now it's a summation as we go from 1 to infinity. Let's do the division. In the denominator, it's k to the power of 3/2. So that's our series Bn we're going to use in the limit comparison test. Any questions at all, folks, producing that series? Okay, looking at that series and going down our list of summary of tests, it's definitely sorry, just figuring out where to park this. It's definitely a P series. And don't let the K's, don't let K's throw you off. It definitely threw me off. Forgot we were dealing with K's here. To make this totally sensible, that should have been a K. Let me fix my work here. A little bit of subscript surgery. I'm going to use this violet color to show the changes. That should have been a K because it's summation of BK. That should have said K goes from 1 to infinity. Oh dear. I guess I get used to N as an index, and it really throws me off when they change that. But like I was about to say, don't let that throw you off. Just because we're using an index K doesn't change the fact it's still a P series right here. It's 1 over K to a power P, but same idea. Our power P is 3/2. So we go over here. Let's say P equals 3/2, which is greater than 1. This implies it converges by the P series test. So we have to test all of our series that comes up. And some of them take a little bit of extra work. Like this one, we had to do some extra exponent work to resolve the actual power to give our conclusion and indicate the test. Once we're there though, that's when the problem starts to take off a little bit better. If we got convergence, then let me see, can I fix that? No, that's a screenshot. Let me come back here and just take it Another screenshot of this. Okay, drop that back down. Should we get just attach? Okay, so the comment I was about to make was, once we know that BN or BK, however we call it, actually converges, it tells us in this problem, they're both going to converge as long as we can show that that limit is true. So those are our next steps. We take the limit as n runs off to infinity of the ratio an divided by bn. On the next step, we're just writing in all of our values. And oh dear, that's going to be a really hard one for me to remember. Feel free to just shout it out if I forget it's k instead of n. It's AK, BK, and k going up to infinity. I've kind of decided I hated k as an index, but it comes up as the homework, so it's here as well in the notes. It's a bit of a struggle for me too, if you find that to be kind of jarring. So limit as k goes off to infinity on our next step. For AK, we grab all that stuff, 2k squared plus k divided by a root 4k squared, 4k to the power 7 rather, plus 3. When it says over here, divide by bk, that means we're multiplying by the reciprocal of that, 1 over k to 3 halves. So times k to the power 3 halves over 1. This is essentially how it always goes when we're comparing to a p-series, because we always resolve to this step, simplifying. But notice it's kind of an interesting one to resolve, even at this stage. Let's keep on going. Limit as k goes off to infinity. We're going to multiply here to here, and that's going to be 2 to the k to the power of, that's 4 halves, times k to the power 3 halves, giving us k to the power 7 halves on that multiplication. Same game on this one. This will be plus k to the power. Over here, it's 2 over 2 plus 3 halves to get 5 halves. And no change in the denominator. 4k power 7 plus 3. We're just about at the stage where we can really kind of pick our adventure on this one. This is one where we can use a shortcut, even though it's not really a rational function, or we could do the full method on this. Anyone happen to know what it would be as a shortcut? This is definitely the dominant term in the numerator, right? What about the denominator? It's k power 7, but because it's being square rooted, we think of it as k power 7 halves for very large values of k. So that's the dominant term in the denominator. That means this has a horizontal asymptote. It is 2 divided by the root of 4. That's a massive shortcut. So let me know if you feel like this needs some logical help to get through. This is a 2 over 2, so it comes out as a 1. But that's great. What we're trying to avoid is 0 or infinity or anything negative. This has to come out as a positive quantity, which is finite. So I'll put greater than 0 here just to remind me that that's what we wanted to see in the limit comparison test. Because that came out as positive, we can now make the statement an, let's take a look, bn or bk converged. I forgot this 1k here. There we go. AK has to also converge because over here we said BK converges as a series. So here's our conclusion. This implies summation AK, which is the summation as k goes from 1 to infinity, 2k squared plus k over root 4k power 7 plus 3, must also converge by, you could say the limit comparison test, but sometimes what people say is by limit comparison. That's a nice way to say it because that's exactly what we did. We took a limit comparison. That's the comparison looking at the ratio. And sure, you didn't necessarily say limit comparison test, but that's what you're implying if you say it this way. So you don't have to follow the instructions to the letter when it says for every test, state the name of the test. just give an indication of what the test is that you're using. Instead of saying, say, P-series test, you can say P-series. Instead of geometric series test, you can just say geometric series. Instead of saying by the limit comparison test, you could say it converges by limit comparison. You're really doing the same thing. But any questions at all, folks, with the conclusion on part B? That's a great question. So thinking about that a little bit more, for very large values of K, just that part survived and just that part right there. And so I visualized it as K power 7 halves canceling out and a 2 over root 4. But to be totally honest, that's not the best answer to that question. The best answer is to show these additional steps. Let's actually do this limit without the shortcut to show how it goes. Does that sound all right? Okay, that's a better way to think about it. And it's one of those things where once you see how it goes in the long form, it kind of shows how the shortcut is really working in the first place. So this is what the steps would really look like. We would take the limit as K goes to infinity of, let's take a look. When we do this using our author's official method, we only go to the denominator and the denominator alone. We take the most dominant thing in the denominator, which is not K power 7, it's K power 7 halves. So we're going to divide everything by K power 7 halves from right here. So it's going to be, let's just write out the full steps. 2 K power 7 halves divided by K power 7 halves plus 2 to the power of 5 halves divided by K to the power of 7 halves. And then over here, when we divide by K to the power 7 halves, we need to factor that into, or distribute it into is a better way to say it, 4K power 7 plus 3. So let's visualize this again. K power 7 halves is really the square root of K to the power 7. That's an important change of view because we go right times K power 7, we can use this idea. Root A times root B becomes root A times B, but the multiplication or division is critical to combine those roots. If we were adding them, the whole thing is off. So, oh, and I forgot to do one thing. We're dividing by K power 7. Sorry about that omission there. It's 1 over K power 7 in that way. So the numerator got divided by K power 7 here and here, and I'm dividing by K power 7 here, or K power 7 halves rather. So now these two combine and we get limit as K goes to infinity. On this one, we just get a 2. So that's kind of nice. Plus, here we get 1 over K to the power 2 halves. So it's just a 1 over K. Now this distributes inside, and so it becomes square root 4K power 7 divided by K power 7 plus 3 divided by K to the power 7 altogether. So next step, we can simplify in our denominator. Limit as K goes to infinity. 2 plus 1 over K square root. Over here, we just have a 4 now. Plus 3 over K to the power 7. Now, because K is going off to infinity, this term converges to 0. And this term, even though it's inside the root, also converges to 0. And we're left with 2 over square root of 4, giving us that 1 altogether. So those are the full steps. And that's essentially what's going on right here. Even the constant is trapped in under this square root right here when we go to use the massive shortcut. And notice it is a massive, massive shortcut for real in the sense that if this was going off to negative infinity, these steps are now critical. If we're going off to negative infinity, the value is not going to work out to a positive one at all. And this estimate would require a negative in front of it out of nowhere, which makes it pretty confusing. Rational functions don't have that same defect, so that's why our author is always more careful with these ones. But if you notice that this is the pattern every single time you deal with a root, you're welcome to take that as a shortcut as well for these kinds of problems. But other questions at the moment, folks, with getting through these? Okay, as far as the limit comparison test goes, I think we're in good shape to attack all the problems on the homework if we want to get started. But there's one problem we haven't done. I felt like it'd be good to do one like that. It's really easy to write down a series where it feels suddenly extremely hard to guess what we even want to compare it to. So when we come back on Wednesday, we'll do the comparison test again with kind of a non-standard example. This one is an unfair exam question, but it could be a homework question. And then we'll do the important work of synthesis. We have a lot of tests, all 6 of them so far. And so we're going to spend some time just kind of reviewing what test matches with what with all those random series before we go off to the next section, which is alternating series test. Well, have a great night, folks. If you have any questions, I'll be happy to help out. Otherwise, we'll come back here on Wednesday, taking a look at part C. Thanks. Have a good one, Rhett.